So hello friends, welcome back to our channel STMetaTronics. In this video we will see how to interface the RGB LED matrix. So these LEDs are not addressable. Okay, so there are two types of RGB LED matrix. One is of addressable LED and another one is non-addressable. So basically we are going to see the interface with the non-addressable LED. So what does it mean that the non-addressable? So each pin of this RGB LED, right? So there are three colors in each pixel: red, green and blue. Three LEDs basically in each pixel. Okay, so the pin outputs, right? So we are taking the common anode. So yes, we have taken the common anode display. So the cathodes, these are extracted out and separately. Okay, so each pixel RGB pin can be controlled individually. Okay, so that can be connected directly, or we can give the PWM pulse also. Okay, so how this works is like, this is the RGB LED. So in the back of the pin you can see that there are multiple pins, connector pins, right? So we can interface these connector pins to control the LEDs. Okay, this is common pin, anode pins. So for each LED the anode pin is common. Okay, now what is the structure of this LED matrix? It is given in the document itself. Okay, so if I zoom a little bit over this, right, you can see that the anode pins of each row are connected. Okay, these are made common. Anode pin of each row is made common. Okay, now you can see that this symbol indicates blue, this symbol indicates red, and this symbol indicates green LED. Okay, now you can see that cathode of, row anodes are made common, column cathodes are made common. Okay, so cathode of red LEDs of each column is made common and taken out separately. Okay, same goes for blue and green LED. Okay, so it will be similar to that, like column anodes are common, and red, blue and green, sorry, row anodes are common for all the LEDs in a row. Okay, anode pins of the LEDs in a row are made common, and cathode pin of the LEDs in a in a column are made common. Okay, so red will be made common, green will be made common, and blue will be made common. Okay, now how we will control that? Like, if you can see that for rows the anode pin is made common. Okay, and for column what they have done is they have connected this red with this red. Okay, so if I highlight this part on the current sheet, right, you can see that the red pins are made common. Okay, for each column. Now if you can see that for the second LED the red is not connected with the column 1 red pin, LED pin. So similar to that, blue and green LED pins are made common also in a column. Okay, so you understood the structure of the pin connections. Okay, now we will see like how we are going to interface the RGB LEDs. Okay, so for that we are going to use the 74HC595 IC. Okay, now what does this mean? 74HC595. Okay, so this is 8-bit shift register IC. Okay, now what this IC provides is basically we provide the serial data, right? We provide the serial data, and the data will be shifted out on the output latches. Okay, now there is, with respect to clock, this IC works with respect to the clock. Okay, so whenever we are going to provide the data serially, the data will be serially ind with respect to the clock input. Okay, now there is one more pin, that is latch pin. So whatever data that we have inputted and shifted, right, that can be latched to the output pins using this latch pin. Okay, so for that we can give serial latch clock. So there are R clock, that is shift clock, and latch clock. Okay, and there is serial data in. So basically we have 1, 2 and 3 pins. So out of these 3 pins, 1, 2, 3, 4, 5, 6 and 7, 7 and 8. So 1 and these 7 pins, total 8 pins are made output. Okay, now we have not taken this QH pin, so that is for shifting out the data again. Okay, out of this VCC and ground will be connected to 5 volt and ground. Okay, serial in will be connected to the microcontroller input. Okay, microcontroller output. Now output enable, this is active low, so that will be connected to ground. Okay, now R clock, SR clock, and this is SR clear. So we have tied this pin to high logic 1, that is 5 volt. Okay, so 1, 2 and 3, these 3 pins will be connected to the microcontroller. 1, 2, 3, 4, 5, 6, 7 and 8, this pin will be connected to as an this pin will be used as an output and will be connected to the LEDs. Okay, so basically if you go and see the structure, right, so it will be connected like this. So we will be giving clock, we will be giving the latch, and we will be giving the data. Okay, serial R clock and SR clock. Okay, now these 8 output pins will be connected to the LEDs. Okay, and we are connecting like here they have connected like this, right, but our schematic will be little bit different. So for to control the each anode, or to power the anode, right, to power the LEDs, we are going to use the PNP transistor. Okay, and that PNP transistor we are going to control using the help of the microcontroller pin. Okay, so this is the structure. I'll just zoom in. So we have used total 24 LEDs. If you see this RGB, right, RGB matrix, there are total 64 LEDs, but due to the limitation of the simulation we have only interfaced 24 LEDs. Okay, so for to control the each row, right, we have used PNP transistor. Okay, now if you see, so all the red, right, red pins from column 1 to 8, this will be connected over here from Q0 to Q7, and Q7 dash will be left open. Okay, same goes for green LEDs, that will be connected to second 74SC 595, and blue LEDs, the cathode pins of blue LEDs will be connected to third IC of 74SC 595. Okay, this master reset is connected to 5 volt. Right, so this is connected to 5 volt, and output enable, it is connected to ground. So all the output enables are connected to ground pin. Okay, now see, first 74SC595 IC, the SHCP, that is shift register clock, right, it is connected to PA0. Data serial in, right, it is connected to PA1, and STCP, that is latch clock, it is connected to PA2. Again shift clock connected to PA3, data that is connected to PA4, and latch is connected to PA5. Now here the shift clock is connected to PA12, data clock is connected to PA11, and latch clock is connected to PA15. So why we have used why we have kept these pins as unused? Because we are going to use the STM32 F401cc, that is a black pill board. So I'll be showing the hardware interface also in the next video. I'll show its simulation and it's working properly or not. So basically to get it working, I have modified these pin numberings. Okay. Now for the PNP transistor, it is connected to 5 volt. Okay, PNP transistor is connected, that is emitter of the PNP transistor is connected to 5 volt. Between emitter and base we have connected a resistor of 4.7 volt. Okay, between the base and the microcontroller pin we have connected one resistor. We can keep its value as minimal as possible. Okay, now the collector is connected to the anode of the row LEDs. Okay, now first thing we will see the simulation is working properly or not. Here we have connected external crystal frequency of 8 MHz. Now we have loaded the hex file. Okay, if we go in design, configure power rails, ground is connected to 0 volt, VCC will be 3.3 volts and VEE is made as 0 because our controller works on a 3.3 volt power supply. Okay. Now I'll run the simulation and I'll zoom in. Okay, here you can see that the green LEDs are working and serially going out, the red LEDs are working and serially going out. Okay, blue LEDs are going and serially going out. Okay, so you can see that there is a pattern, right? I'll just make this low. So you can see that there is a pattern going on, right? Green blue, red blue, right? Then green red or red green, then green is running, blue is running. So we have created an animation of running LEDs. Green is running, blue is running, right? Now this is red is running. So we will see, now we will see the coding for this. Okay, so coming to the coding part, we have included this RGB LED.h. Now we have written it ourselves and we will go and see the context of it. Okay, now coming to the main part, we have made some pins as low. Okay, now coming over here, see, to control the first row of LEDs, what we have done is HAL GPIO write pin, port B, pin 0, we have made it as 1. Okay, and we have made the rest of the 2 pins as low. Okay, so it will run continuously. Now there is a run LED pattern number 8, right? Run LED pattern number 9, and there are total 6 LED patterns that we are running on one row. Okay, so if you can see that there are multiple patterns, right? Multiple rows. So after doing that we are going for the second row, and after doing that we are going for the third row, right? Now we have kept it as it is. We'll see the pin configurations. So as I have mentioned, for this simulation and for this project we are going to use the black pill board. Okay, that is STM32 F401cc U6 controller. Okay, now PA0, 1, 2, 3, 4, 5, 11, 12 and 15, PA15. Okay, so these pins are connected as an output port, GPIO output port. Okay, so we have configured these pins as an output port. Now PB0, 1 and 2, these are also connected as an output port, configured as an output. So all these pins we have made an push-pull, output push-pull. Okay, and we have connected a pull-up resistor, internal pull-up resistor for all the GPIO output pins. Okay, now coming to the clock configurations, we are using the internal RC clock. Okay, we are using the PLL clock source. Okay, and we have made the system clock 70 megahertz. So using this 16 megahertz clock frequency of internal RC oscillator and using the PLL source mux, we have made the system clock source as 70 megahertz. Okay. So for that, the PLL multiplier and the divider. Okay, two-stage divider. So this is the configuration for it. Okay. So apart from that, we have not configured any other peripheral. Okay, apart from the GPIO, we have not used any other peripheral. Okay. Now, once you do that, click on device configuration. It will generate your code. Okay. So our main.c code is fairly simple. Now we will look into our RGB LED.h file. Okay. Now see here, right? For SHCP, right, shift register, shift clock, we have used PA0. For data, we have used PA1, and for latch, we have used PA2. Okay. So we have defined the macros. The same pins we have defined in the macros, right? So hash define red SHCP, red DS, and red STCP. So pin 0, 1, and 2. Similarly, for green LED, we have used pin 3, 4, and 5. Now for blue LED, we have used pin number 12, 11, and 15. Okay. So for blue LED, this one is the third that is connected to blue LEDs, right? Pin number 12 is connected to SHCP. Pin number 12 is connected to blue SHCP. Pin number 11 is connected to blue DS, right? Data in, right? And pin number 15 is connected to STCP, blue STCP, right? Blue STCP, right? The ports that are used, that GPIO ports that we are going to use for this simulation and the project, it is for LEDs, it is port A. So we have kept it as port A. Now we have declared some functions, right, using which we are going to display different patterns, LED running patterns, right? So yeah, now we will go, this is for the RGB LED.h file, header file, right? Now we will go into the C file, .c file. First thing that we have to include is the header file for this RGB LED.h. Okay. Now we want to initialize the LED display matrix, right? So LED panel initialization. What we have done is we have made STCP reset, that is the initial state will be low. Okay, the latch clock, that will be low. Okay. Now to make the red, or to display row 1 red LED pattern, right, we have used shift pattern. We have given the value, okay, that will be displayed on port A, DS, data in, and SHCP. Okay, these are the parameters for this shift pattern function. Okay, then we have used the latch output, that is GPIO A and red STCP. Okay. Now see, this is red, this one is green, and this one is blue. Okay. If you see that the code is almost similar, okay, just these arguments, okay, arguments name is different. So for shift pattern, for red LED, this will be shifted on red. Okay, red LED data in. Okay, for green it will be shifted on green, and for blue it will be shifted on blue. Okay, the clock will be provided on shift clock, SHCP, red SHCP. For green it will be green SHCP, and for blue it will be blue SHCP. Okay, once all the 8 bits are shifted, right, the pattern is shifted, we have to latch the clock. So we have given that latch output red STCP. For green it is green STCP, and for blue it is blue STCP. Okay. Now for latch output, right? These are the functions for the latch output. We have provided two parameters, that is the pin port and value, pin variable. Okay, so for that we have used GPIO pin toggle, right? Pin port and pin value. Now in GPIO pin toggle, whatever pin port that we have provided, it will tell it as GPIO A, okay, pin var, and it will set it first, give some delay, and then it will reset it. Okay, what we can do is we can directly use this as GPIO A pin port over here directly. Okay, now coming to this shift pattern function. Okay, now see LED pattern, whatever pattern we want to display, then it will be pin port, data pin, and SSCP pin, which SSCP pin we want to use, right? So there are total 8 bits. We want to shift the data for 8 times, right? Now we have used a for loop which will run for 8 times. Okay, now LED state, so whatever pin, like whatever data we want to shift in, the data must be shifted in, right? So higher bit MSB will be shifted in first, then the lower bits. In the last thing, the lower bit will be shifted. Okay, so LED state pin 01. Okay, this is LED pattern. First LSB is shifted. Okay, it is shifted, then we have given whatever LED state that we have, pin state, data pin, and pin port we have shifted. Okay, now LED pattern, we have shifted the LED pattern by one. Okay, so again we are shifting whatever pin port, SSCP pin, right? And pin toggle we are giving, here we are giving the clock. Okay, here we are setting the pin state. So LSB is sent first, then bit 1, bit 2, bit 3, and in the last MSB will be sent. Okay, so likewise we have made our code. Okay, so this is shift pattern. Now I'll explain in more detail. Okay, so for here we have understood, we have taken two local variables. Okay, we have taken a loop, for loop, which will run for the 8 times, right? Now this LED state, we want to set the pin, like we want to shift the data serially, so there must be we want to shift the data bit by bit. Okay, to get the bit, like we have used this AND operation. So LED pattern and 0x01. So whatever the LSB is, that will be the LED state. Okay, so it will be either 0 or 1. So that LED state we are giving, and then we are giving the clock as shift clock. Okay, now again we are shifting this LED pattern, right, shifting it by 1. Okay, then we are getting the LSB, we are getting assigning it to the LED state, and then we are giving the clock. Okay, so likewise 8 bits will be shifted. Now here it will be shifted from LSB to MSB, not from MSB to LSB. Okay, so this is shift pattern function for us. Okay, now coming to the row 1, red green pattern. Okay, so see what we are doing is shift pattern, red LED value. Okay, then GPIO, red LED data in, and red LED SSCP. Okay, then we are using the green LED pattern, green GPIO A, green data in, and green shift clock. Okay, then we are latching the red and green both. So for likewise we have written multiple LED patterns. Okay, so these are the patterns that we have written. Okay, I'll paste the content of this RGB LED.c and RGB LED.h in the description. Okay, that will be easier for us to understand the code and to reuse it. Okay, So after completing this, we are simulating. Okay, so we are calling these different patterns over here in our simulation. Okay, in the while one loop. Now we'll generate the code. We'll go over here. Okay, and we'll load the code. So here you can see the LEDs are running different patterns. So here you can see that now the row is switched. So you can see that there are multiple LED patterns that are running on this. Okay, so you can configure your own LED pattern and switch it. Okay, in the next video I will show that we have implemented it on the hardware and it is working perfectly fine. Okay, so we will try to display the image on it, some text image and some animated images also. Okay, so for that what we need to do is we'll see that in the next video. Okay, so that's it for this video. If you like the video, if you like my explanation, please give it a like, share with your friends, and thanks for watching the video. We'll see you in the next video.